Now that we have actually seen how the struct looks like, I mean, let's just look at a graphical figure of how the task list looks like. You basically have the struct task struct, which is basically described each thread, and you have a doubly linked list, so you have it linked to the one that follows and the one that is before it, and this is basically your task list. So it's a circularly double linked list, and this is it has some few details that might be a bit different from what you have studied in your algorithms, but the concept itself is exactly the same. I mean, the implementation might be different, but the concept itself is exactly the same. And as we have spoken about that there are different process states, so if each one of these processes slash tasks slash threads can be in one of many states basically. And basically the way that a thread starts is that some existing task calls fork and creates the new process slash the new thread slash the new task. I mean, they are all equivalent in Linux. I cannot emphasize that more. And then you basically go into a queue of tasks that are ready to run but not running yet. Okay, and everything here in capital is basically a flag that stores the state of your task. So by setting the task running state to something, like for example, if you remember here, we had the state as unrunnable, runnable, or stopped, for example. So this basically says that, okay, this is runnable, unrunnable, or stopped. And it will lie based on what you set to some of these states basically. So you have some task well, some number of tasks that are waiting to be scheduled on the processor. Once the scheduler dispatches one of the tasks to run, and that's basically by calling context switch, a function that you can actually search for in your code, in your Linux kernel code, you basically move to a running state. And in your running state, you have one of a few options. You can be preempted and go back to ready to run, but not running. And that's basically if you get something like timer interrupt. And we have talked about the timer interrupts as basically you allocate some time for the process to run on the processor, and after that time you evict that task so that other processes get also some share of the processor. And that's your virtual processor abstraction. Okay, but it can be also that you got some higher priority task interrupting your work, so you move that task there and you move the higher priority task here. Okay, the task can finish also, so task gets terminated, and that thus it calls do exit. We're going to discuss this in a bit more details. And the task can also be blocked on some data, for example, fetching data from memory or fetching or opening some file from hard disk. And I mean, from the hard disk, you typically read into the memory because that's the only path you have. So I mean, you might get blocked for a few milliseconds or even seconds waiting for something to happen, waiting for a network packet or something. And then the task sleeps on some wait queue for a specific event. And you wait here in the wait queue, and there you have basically two flags that you might want that basically control what triggers you to go out of your waiting, and one of them is task interruptible and the other is task uninterruptible, and we are going to discuss them in the next two slides. But anyway, so moving from task interruptible or task uninterruptible, which are basically both meaning waiting, some event happens and you basically go back to the task running state and then wait for your time to get scheduled on the processor. So what is task interruptible and what is task uninterruptible? An interruptible task is basically a task that is sleeping and that can get that can move from the sleeping state, from the waiting state to the runnable state. either when some condition exists, so you're waiting for a network read, for example, or for a file to open, but also the process can wake prematurely and become runnable if it receives a signal. And that signal basically can be, for example, I mean, you might be waiting for some event to happen, but you can also wait for a signal that comes from the actual kernel. And that signal can be something different, okay, than just waiting for the event to happen. So you can get moved to the task running state by either of these two conditions. One of them is that you're waiting for some condition to exist, some event, and waiting for a network packet to arrive. Okay, that's one way. But the other way is that the kernel wakes you up for some reason. Okay, and that reason is, of course, very dependent on your thread. Okay, and a task uninterruptible is exactly like a task interruptible, except that it only wakes up when the condition happens. Okay, and it cannot wake up if it receives a signal from the kernel. So the only way for this thread to rerun is to basically, or to go from the waiting state to the runnable state. The only way is for that event to happen. Otherwise, it will stay in the waiting state. And this is used in situations where the process must wait without interruption. I mean, again, it's very program specific, and or when the event is expected to occur quite quickly. So you expect that, well, this event is going to happen in a blast. So you then put it as task uninterruptible. But in general, you use this flag much less often when you basically are doing threading inside the kernel. Okay, when you're playing with the actual kernel, you use that flag much less often because it basically reduces your chances as a thread to move from a waiting state to a runnable state.